The chain rule says the derivative of f of g of x is f prime of g of x times g prime of x. So let's prove this just by using the definition of the derivative and following our nose. And let's see how it goes. This is not going to be an elegant short proof. It's going to be kind of a trudge through the mud and fix any problems that happen kind of proof. But I like this proof. You don't have to introduce any unfamiliar notation. And it's more like what happens when you sort of do mathematics yourself and try and prove things from scratch yourself. So you run into problems and then you fix them. So let's see. Let's define a function, let's call it s of x to be f of g of x, and then we're going to take its derivative. Here we go. By definition, the derivative of any function, limit as h approaches 0 of s of x plus h minus s of x over h. And here we have s of x equal to f of g of x, so we got f of g of x plus h minus f of g of x all for h. Okay. So now in order to continue from here, we're going to need some of these f's and g's to kind of get pulled apart in a sense, because we have these two pieces here. There's a product in here, right? So what I'm going to do is some kind of wishful thinking. I'm going to say, well, I have this g prime of x out on the right-hand side, so I want to make that appear out here. Well, g prime of x is the limit as h approaches 0 of g of x plus h minus g of x over h. So I want a g of x plus h minus g of x over here. So I'm just going to say, well, hey, let me just put it there. All right. But obviously, I can't just multiply by g of x plus h minus g of x, but I can multiply by g of x plus h minus g of x over the same thing, right? It's a fraction. I can multiply the top and bottom by the same thing. And I'm going to introduce some extra stuff I don't want, but we'll deal with that later. I'm going to multiply the top and bottom by g of x plus h minus g of x. And now I'm just going to move things around. I'm going to put these together because I want to get the derivative of g. I want to get g of x plus h minus g of x over h. So I'm just going to swap the order of multiplication in the denominator to make that happen. So I have f of g of x plus h. Same thing here, f of g of x. But now I'm going to put this over g of x plus h minus g of x. And the second part, I'll leave the numerator the same as well, g of x plus h minus g of x, but over h. So I just swap the order of multiplication in the denominator. And now this thing looks like g prime, which is exactly what I want out here. All right, so I'm going to break up this limit into two limits. Limit of the first factor and the limit of the second one. And the limit laws tell me I can do that as long as both limits exist. So g of x plus h minus g of x over h. And now this guy right here, this is indeed g prime of x. So I have my g prime of x out here, okay? And of course, I'm allowed to do this as long as both limits exist, but this limit exists because I'm assuming that when I do this rule, I'm saying the derivative of f of g of x is f prime at g of x times g prime of x. So what I'm saying is that when both sides are defined, they're equal. And so if this right-hand side is going to be defined, I need to be able to take the derivative of g at x. So this limit exists. It's g prime of x, right? So the question is, what is this thing? Well, if I look at the chain rule, again, keep my eyes on the prize, it's got to be this, because I have the g prime of x right here. So this guy, it has to be f prime at g of x. I just have to somehow show it. So that I'll be done this proof if I can show that this thing is f prime at g of x. Well, is it immediately? Let's see. What is f prime at g of x? Well, remember that f prime at, say, heart, right, the definition of f prime at heart is limit as h approaches 0, f of heart plus h minus f of heart over h. So usually that heart, I'd call it x, but you could put any number there, or any letter, right? Or any thing, any blob could go there. So that's the definition of f prime at some value, any value you like. So in particular, f prime at g of x, what's that? Well, I'm just replacing all these hearts with g of x's. Limit as h approaches 0, f of g of x plus h minus f of g of x all over h. So unfortunately, these are not the same. At least they don't look the same. They have to be the same if the chain rule is true. So to finish the proof, we have to show that this thing is equal to that thing. So that's our goal now. If we can show that this and that, this limit and this limit give you the same value, then we're done. So let's try that. So writing it out, let's see. We need to show that, let's see, the first one, this one right here, right? Let's write it out. Limit as h approaches 0, f of g of x plus h minus f of g x over g of x plus h minus g of x. So is that equal to the limit as h approaches 0? What's the second one? This one right here. F of g of x plus h minus f of g of x over h. Okay, good. Now notice the differences. In here, they're similar. I've got this f of g of x over here. In here, the plus h is inside the brackets, and here it's outside. And here we have a totally different denominator, g of x plus h minus g of x, and here just h. So I mean, I wish this h could just escape the brackets. Okay, but that's not how it works, okay? So I need to show somehow that these things are equal. So to do that, what I'm going to do is define a new letter for this denominator. Let me call it k. So let k equal g of x plus h minus g of x. And that way I'll have a single letter for the denominator here, so it'll kind of look more like this one. I'll have an h here and I'll have a k here. And then you see, if k is equal to this, then also in here, this g of x plus h, I can rewrite that in terms of k as well, because I can isolate g of x plus h. So if I let k be this, then I also get g of x plus h in terms of k by moving this g of x to the other side. So if I move the g of x to the other side, I have g of x plus k. All right. So rewriting this guy, I now have the limit as h approaches 0. I'll just rewrite it here. F of g of x plus h minus f of g of x over g of x plus h minus g of x. And now I make those replacements. I say, okay, the denominator is now just going to be k. So that's what k is. And then g of x plus h is g of x plus k. So this g of x plus h in here is going to be g of x plus k, right? Or yeah, this g of x plus h right here. G of x plus k minus f of g of x. All right, and now look at these. These look the same. The only difference is here I have h, here I have k. However, here, look, again, limit is h approaches 0, and I still have a limit as h approaches 0. So here the problem is, I've got these two letters, h and k. If they were all h's, I'd be fine. But also notice, if they're all k's, I'm also fine. Because the value of this limit doesn't depend on the name of the letter h. H is just some variable that's going to 0. H could be t, h could be p, h could be any letter you like, okay? Z. The value of the limit wouldn't change based on the name of this variable that's going to 0. I could rename that variable. Everything would be fine. So if this was a limit as k goes to 0, I would be fine, and I would be done. Because then I would really be showing that these two limits are equal. I started from this one, rewrote things in terms of k. And now look, what happens? Well, as h goes to 0, what happens to k? Well, we can see by looking right here. As h goes to 0, let's see. As h goes to 0, well, look what's happening here. X plus h gets closer and closer to x. So this number, x plus h, it's a number that's approaching x. And so this g of x plus h is, I'm evaluating g, but at numbers that are getting closer and closer to x. And so as h approaches 0, this x value is getting closer and closer to that one. And so the difference between them should be going to 0. As long as what? You need something here. As long as g is a continuous function at x. If g is continuous at x, that means as you approach x from both sides, the limit is the same as what you get as if you just plugged in x. So as this x plus h gets closer and closer to x, g of x plus h should get closer and closer to g of x. That's true as long as g is continuous at x. So, and g of x plus h approaches g of x if g is continuous. G is continuous. But is g continuous at x? Is that okay? Is that an extra hypothesis we need to add here? Well, look back at what we're proving. We're proving this rule. And so we're proving that this left and right hand sides are equal when they're both defined. So I'm assuming that this rule is saying the derivative of that is equal to that, as long as you can actually, as long as this is defined. If this is defined, then g prime of x is defined, so g is differentiable at x, and therefore it's also continuous at x. So that's fine, g is continuous at x. If this chain rule is going to work as I wrote it, then we have to assume g is continuous at x, and we have to assume g is differentiable at x. And so it must be continuous there too. Great. And therefore we can say that the limit as h approaches 0 of this thing, just rewriting this limit right here, minus f of g of x over k, this is equal to the limit as k approaches 0. So this is a little k down there, clear, of the same thing. Of g of x plus k minus f of g of x over k. Because as h approaches 0, we concluded that this quantity k approaches 0 as well, because this gets closer and closer to that, the difference goes to 0. So as h approaches 0, k approaches 0, and so the limiting quantity, the limit of this guy as k approaches 0, limit as h approaches 0 of this is the same as the limit as k approaches 0 of this, because as h approaches 0, what happens to these k's? Well, they're going to 0. Good. And now looking at this. This limit, it is really the same as that limit. There's a letter h here, there's a letter k here, but as I mentioned before, the value of the limit shouldn't depend on the name of that variable. So this thing right here is that thing right there. And what was that? That was f prime of g of x. So we're done. We showed this limit is equal to that one through this argument here. So this guy right here really is f prime of g of x, and we're done. To recap, we defined s of x to be f of g of x. We took its derivative using the definition. multiplied the top and bottom here, broke it up into two limits. The right one was g prime of x, the left one was this guy, and then we showed that this guy actually, if you define this thing k and you go through the motions of rewriting everything in terms of k, you get f prime of g of x. So we got f prime of g of x there, what we wanted, times g prime of x. We're good. Now that proof almost works. However, there is a problem. Maybe some of you might have caught it. It's right at the beginning. Here, when I did this bit of wishful thinking, multiplying the top and bottom by g of x plus h minus g of x, in order to get this g prime of x to pop out on the right, in particular, I divided by something. And every time you divide by something, you have to be careful that you did not divide by 0. So the question is, could I have divided by 0 here? Oh, yes. It is definitely possible to divide by 0. If g takes the same value at these two different numbers, x plus h and x, then I'm dividing by 0. Now, it's not unusual to be evaluating a limit where when h equals 0, the denominator is 0. That's totally normal. You get these indeterminate forms like 0 over 0, and you can still simplify evaluate the limit. But this could be much worse, because imagine, for example, say g is a constant function. So say g of x equals 2. Well, then no matter what numbers you plug in to g, it always spits out 2. So these are just both 2's. And so you're literally dividing by 0, not by a function that takes the value 0 at a point, but by the number 0, the constant 0. And so it's not just the case, if g is a constant function, it's not just that when you plug in h equals 0, you're dividing by 0. For any value of h, you're dividing by 0. And so we're trying to evaluate this limit as h approaches 0, but this expression, it's undefined even for values of h that aren't 0, even for h equals 0.1, for h equals 0.7, for h equals minus 0.01. Actually, if g is a constant function, this is undefined for any value of h. As a function of h, like if you plug in different values of h, the domain of this is empty. There's no graph. Okay, so it doesn't make sense to evaluate the limit of a function with an empty domain. There's no graph. So if division by 0 here is a real problem. As long as I don't divide by 0, this proof is totally fine. So say, for example, g is a function that's always increasing. Well, then this number is always going to be bigger than that one if h is positive, and smaller than that one if h is negative. But the point is that if these two numbers are different, then I'm not dividing by 0. So this proof works sometimes. It works as long as g is an increasing function, for example, a function that's always increasing, or a function that's always decreasing. But in general, this is a real problem. I want this chain rule to work all the time for any functions f and g where this side is defined. I don't want it to only work sometimes. So we have to fix this problem. So how can we do it? Well, I will show you a way to do it. I am going to define a new function. So our problem, okay. I'm going to fix this problem. What is the problem? The problem is we could have g of x plus h equals g of x way back at the beginning. And that's something I want to avoid. I don't want to divide by 0. So I'm going to define a new function, and you'll see exactly why I'm doing it this way in a sec, called q of t. Let's call it q, say. And it looks like this. It's f of t minus f of g of x over t minus g of x if t is not equal to g of x. And it's f prime at g of x if t is equal to g of x. Okay. So, why did I do this? Well, this function q, the idea is this function q, when I actually evaluate it, I'm never going to divide by 0. And the reason why is because what would I have to plug in to divide by 0? Well, here I'd have to plug in g of x. That's what would make this denominator 0. If I plugged in g of x, then... Oh, but wait, g of x, it wouldn't go in here. It would go in there. Ah, okay, and there's no division here, so we're fine. So this is a function which, if you think about it, whatever value of t you plug in, it's never going to be undefined. And the reason why is because you're never going to divide by 0, because if you plug in the value where you do divide by 0, then it goes in here actually. It never goes in there. So you never do the division. And it might seem weird to define it just to be f prime of g of x here. But I can do that. Remember that I'm trying to prove this quotient rule. Sorry, the chain rule. And in order to prove it, right, what I'm proving is that the derivative of f of g of x is f prime of g of x times g prime of x. So I'm assuming that these things are defined. I'm assuming that this number is a well-defined number. And so the way we're going to use this strange function q is we're going to say, okay, look at this. Instead of showing that this thing right here is equal to this, which was problematic because I might have divided by 0, I'm going to show that this thing right here is equal to something very similar. So we need to show that this expression right here that we did this manipulation to where we could have divided by 0, so that's f of g of x plus h, just copying it from the very beginning, minus f of g of x over h is equal to q of g of x plus h times g of x plus h minus g of x over h. Now look, I have this guy here, and when we did this manipulation, we ended up with this guy times this guy. But in here, this is where the division by 0 could happen. And so I want to take out I want to redefine things so that this division by 0 can't happen. So if you look here, q of g of x plus h. If I evaluate q of g of x plus h, well then look, if g of x plus h is not the same as g of x, it goes in here. And when it goes in here, what do I get? F of g of x plus h minus f of g of x over g of x plus h minus g of x, which is exactly what's here. So as long as I'm not dividing by 0 here, this q of g of x plus h is giving me the same thing I had here. But if I am dividing by 0 there, sorry, if I'm in here, if I am dividing by 0, well then that happens when g of x plus h is equal to g of x. So then this g of x plus h, I put it in here. If it's equal to g of x plus h, oh, I don't divide by 0. I just get the value f prime of g of x. And so what I need to check is if this works, then we're going to be good. So let's just confirm that this works, okay? We already kind of went through it, but let's write out the details. So I have two cases to consider to check that this works, because I have these two cases right here in the piecewise function. So does this work? Well, if g of x plus h equals g of x, then let's see what happens. Then what do we get? If g of x plus h equals, sorry, let's do this case first. If g of x plus h is not equal, we're going to have to do the other case in a second. But let's say they're not equal, okay? Then q of g of x plus h is equal to, well, because we're assuming g of x plus h is not the same as g of x, we're in this case, so we get f of g x plus h minus f of g of x over, okay, we're plugging in the g of x plus h, so it goes in there, g of x plus h minus g of x. And so this equation right here, that's exactly what we showed right at the beginning. Right? That's exactly what this manipulation showed. We went from here down here, and that's exactly what we got. This is equal to that times that. And that's just what this says, because this piece right here is the same as it was at the beginning. Okay, so we already showed that. So we already showed this equation works. Right. So we showed the equality holds already, because we're not dividing by 0. On the other hand, if g of x plus h is equal to g of x, well, that was where this problem happened. That was this division by 0. But now in this new inequality, equality, this new equation, where instead of having this guy there, we have the q of g of x plus h, then let's see what happens. So in that case, when these two things are equal, when we evaluate q of g of x plus h, let's see what happens. Well, q of g of x plus h, q of t is equal to this, so I go through here and I'm evaluating q of g of x plus h in the situation where g of x plus h is the same as g of x. So I'm in the second case, because I'm plugging in something which is the same as g of x. It goes in there. Oh, and then what comes out, well, just f prime of g of x, right? Because I have g of x plus h is indeed equal to g of x, so it spits out this. So we have f prime of g of x. Okay. And now, look at this equation again. If we're in the case where g of x plus h is equal to g of x, let's look at both sides of this equation and confirm that they're still equal in the second case. Well, look at the left-hand side here. If g of x plus h is the same as g of x, then on the left-hand side, we have, let's write it out, f of g of x plus h minus f of g of x over h. I'm going to do sort of this in two pieces, you see. Well, we're in the case now where these two things are the same, the two inputs to this f. So we've just got f of g of x minus f of g of x over h, which is equal to 0 over h. Okay? And that's equal to 0, as long as h is not equal to 0. Okay? Now let's look at the right-hand side of this equation right here. We have that q of g of x plus h is f prime of g of x. So on the right-hand side, we've got q of g of x plus h times g of x, I'm just copying it out, minus g of x h. But this thing is f prime of g of x. And this thing is g of x minus g of x over h. Because we're in the case where g of x plus h and g of x are the same. Okay? And so we end up with f prime of g of x times 0 over h. And because this is just some number f prime of g of x. It's the derivative of f evaluated at g of x. And as we've mentioned before, we're assuming that this is something that's defined. So this is defined, and this is some real number. So when I multiply by 0, I still get the 0 for h. And once again, this is 0 as long as h is not equal to 0. Okay. So in conclusion, what have we done? We've showed that this, we've showed that this equation holds. In any case, we did the case where g of x plus h and g of x are different. In that case, we're fine. That's the thing we showed in the first place, is when you don't divide by 0. And now if you do divide by 0, with this new definition, this new thing, q here, is q of g of x plus h, instead of this thing, then even if you are plugging in, even if g of x plus h and g of x are the same, so you would divide by 0 up here, you don't divide by 0, and in fact, you get this equation, it's still true. So this equation is true all the time, and you never divide by 0. So, to finish off the proof, all we got to do is, remember, go back to the beginning. Where's the beginning here? We were taking the derivative of this function right here, s prime, and it was the limit as h approaches 0 of this thing. So we're doing the limit as h approaches 0 of this thing. So looking back at the beginning, so we have s prime of x, it was the limit as h approaches 0 of this stuff right here, f of g of x plus h minus f of g of x over h. And we just showed that this is always equal to that. So we confirmed this is q of g of x plus h times g of x plus h minus g of x for h. All right. And so to finish off, we're going to break this limit up into two pieces like we did before. Q of g of x plus h times limit as h approaches 0 of g of x plus h minus g of x. Oh, sorry, going to different here. Over h. All right. Cool. Now, what is the limit as h approaches 0 of q of g of x plus h? Okay, well, looking back here, we have q of g of x plus h, in this case, was this guy. And we showed that the limit as h approaches 0 of that guy was f prime of g of x. That was the first part of our proof, right? So we showed. So in this case, the limit of q of g of x plus h is the limit of that guy as h approaches 0, which is f prime of g of x. That's what we showed at the beginning. Well, in the middle, I guess. And now, what if g of x plus h is equal to g of x? Well, q of g of x plus h, it is f prime of g of x plus h also by definition of the function q. So this function q, regardless of whether you're in this case or in this case. If you're in this case, the limit as h approaches 0 of that guy is f prime of g of x. We already showed that. If you're in this case, the limit as h approaches 0, did I say x before? It should be h. The limit as h approaches 0 of q of g of x plus h is the limit as h approaches 0 of this guy, which is f prime of g of x. We showed that before. And if you're in this case, the limit as h approaches 0 of this guy is the limit as h approaches 0 of this, and this is already f prime of g of x. There's no h in there. So in either case, the limit as h approaches 0 of this guy is f prime of g of x. And the limit as h approaches 0 of this guy, of course, that's the definition of the derivative of g. So there's the chain rule.